Our topic is talking about the first law of Newton and its applications. The first law of Newton is the law of inertia. The law says that a body at rest will continue to be at rest, and a body in motion will continue in motion with constant speed unless acted upon by the net external force. The key word is continue. If the body is at rest, then it will continue at rest. When the body in motion with constant speed, it will continue moving with constant speed unless acted upon by the net external force. If we have an object placed on the table, this object will remain at rest unless acted by the net external force. So therefore, the body will be at will body at rest will continue to be at rest. But the requirement, meaning, in other words, because this is at rest, so therefore the net external force should be zero. To satisfy this statement that the net external force is zero, this must meet the requirement. How can we say that there is no net external force? How can assure that there is no net external force on the object? Then we have to use the three-dimensional axis because we are living in the three dimensions. Therefore, this object might move along the x-axis, or maybe might move along y, or both, or move along z-axis. Z-axis means towards you or towards the monitor. Our x is towards this side, then in opposite side. Up and down is our y. So therefore, if we say that the net external force is zero, it must satisfy the three conditions. The sum of all forces along x must be zero, and the sum of all forces along y should be zero, then the sum along z should be zero. So this should be zero. If this three statement zero, then therefore the net external force is equal to zero. In the next statement, a body in motion will continue in motion with constant speed unless acted upon by net external force. If we consider a rough surface and place an object on the upper end of the inclined plane, then release the result, the object will stop at a certain point. Why? Galileo said it's because of the opposing force called friction. If we improve the surface and change the rough into smooth surface, then release an object on the upper end of the inclined plane, then it will stop at the distance far from the stopping point of the rough surface. The answer is, Galileo said that because the friction is less than compared to the rough. So therefore, the opposing force is less than compared to the surface in on the rough surface. So therefore, it has a greater displacement. Now, if we imagine that suppose there is no friction on the surface. Now remember that it is impossible to have frictionless or zero friction, but we can provide a frictionless surface by improving the contact. So if we imagine that there is no friction between the rolling object and the surface, then just like this, if we have no friction, then therefore releasing an object on the upper end and it will move forever. So therefore, the object moves at a constant speed without stopping unless acted upon by net external force. So a body in motion will continue in motion with constant speed until acted upon by the net external force. So what are the evidences of this theory or this law? What are the examples? Example is, remember that the moon rotates around the earth at a constant speed and it won't stop until now. It is rotating in at least 30 days. around the Earth. So therefore, the moon is moving at a constant speed. Why? Because the net external force is zero. So if someone holds the moon, then that's the time that it won't move at a constant speed. And take note also that Earth is moving around the sun, and we are rotating around the sun for about 365 days. So we are moving at a constant speed around the Earth. So therefore, it is because that there is no net external force while moving around the sun. So this is the great evidence of the first law of Newton. So therefore, the net external force is zero. So therefore, it must satisfy again the three conditions. Summing up all forces along x is equal to 0, along y is 0, and along z should be 0. And this is also the definition of equilibrium. We call this as static equilibrium. Whenever the object is at rest, then it is said to be in equilibrium. So therefore, when we are telling us about the equilibrium, then the net external force should be 0. So, in order to understand this law, let us have the application problem. The problem says that you are asked to find the tensions in the surface. In this case, we have only string, so therefore, let us say tension in the string, whose mass is 30. The object was hung on by means of a string, and this is a 30 kilogram mass. So the question is, what is the tension? Tension is the force experienced by the string. Remember that the string is holding only a tensile force. A string cannot hold compressive. It is only a tensile. When you stretch a string, then it reacts and it holds a maximum depending on the quality of the string. So suppose the string is capable of holding the 30 kilogram mass. The question is, how much is the tension? So to answer this one, this is very simple because we have only one string. So we call this as the object is in static equilibrium. So if it is in static equilibrium, then it should be in the first law that the net external force is equal to 0. To answer theoretically and provide the exact solution of this, we will use the first law of Newton. All you need to do is to identify all the forces acting on this object. What are the forces along the, exerted on this mass, 30 kilograms? We have the force downward. Okay, so all you do is to overlay the Cartesian, say that the weight is toward, so therefore this is a negative. And remember, weight is the product equal to the product of the mass times the gravitational acceleration. So therefore, 30 times 9.81 kilogram meter per second squared is Newton. So it is directed downward, which means that this force is a negative force. And since the object was connected in the string, and the string reacted upward, so therefore there must be a tension on that string, called it as T. So T corresponds for tension, and this is the weight. So therefore, there are only two forces acting on this object, the weight downward and the tension upward. So weight is mass times gravity. Then applying the law, the first law of Newton, summing up all forces should be 0. So the three axes must satisfy to 0. So therefore, we can utilize, in this case, we have only one axis that has force. We have only the y-axis. The z-axis, we have no force along z towards you or towards the screen, and we have no force along x. So the only force present is only forces along y. We have the upward, we have the downward. So therefore, the x and z are set to be 0 automatically. So therefore, in order, because this is at rest, so therefore, we can sum up everything, all forces along y. So summing up all y, so we have y, this is positive, t is positive, and w, this W is downward, so therefore this must be negative. Since there are only two forces, then equate to zero. This is according to this definition. If you sum up all forces along Y, summing up positive T minus W, the sum should be zero. Then transpose this W to the right side, then replace W with mg, substitute the values, the 30 kilograms for the mass and the 9.81 for the acceleration of gravity, or gravitational acceleration of the Earth is 9.81 meter per second squared. Then the result is 294.3 newtons. This is the tension in the cord, which means that whatever weight, the weight is always equal to the tension of the string. So the weight is downward, then the tension is upward. Okay, very simple because we have only one string. Now let's elevate this problem. Let us say in problem 2, what will happen if not only the string holds the mass. Suppose I have another string attached, is maybe in between of this. Then what will happen if I attach another string and I will stretch that horizontally, then fix it on the wall. So assuming this is horizontal, and this string now has an angle from the horizontal axis be equal to 30 degrees. This is still 30 kilograms. So the question is, what are the tensions in the string? Tension is in the string. So therefore, there are, at this point, this is the intersection of the three strings, no? So we have this one horizontal string, and we have this inclined at a 30 from the horizontal, and we have the vertical string which was connected to the weight. So we have three strings, but this string is the same as the weight. Okay, this is the same as the weight, the same as, because the weight is still 294.3. So therefore, we already know that the string here has the tension of 293. So our task is to calculate the amount of tension in this cord and also this cord. Okay, the question is, are they have the same force applied? The answer is not necessary. Why? Because this is horizontal and this is inclined. So the question is how much. So now, to answer this problem, what is the tension in the string? We need to use the law. And the first law of Newton is applicable to the problem. Why? It's because that the object, the mass M, was in the rest position. So therefore, this belongs to equilibrium, static equilibrium. So the force should be zero. Now in this case, again, we have only the two axes. There is no force along Z. But this time, we have the force along X and force along Y. Because this string has a component along X and component along Y. So all we need to do is to overlay the Cartesian at the point of intersection of the strings. So place the Cartesian at that point, means this is the origin, and this is the X, towards right, towards left, negative X, upward, positive, downward, negative Y. So then next is you have to provide all the forces. What are the forces on the intersection point of the string? So first we have the weight. Take note, the weight is mass times gravity. The weight of the string, or the tension of the string is the same as the weight. So therefore, this is downward force. While this one is the force on our horizontal force is towards right. Okay, because tensile force. So therefore, at the point of intersection, the force will tend to move away from that point. So therefore, we have this also, this one, this is call this as T1, then this is away from the point, but this direction is 30 degrees from the horizontal. So this is 30 degrees. Now T2, our T2 is towards the right directly. So therefore, this is along positive x directly, and this is, it has a component along x and component along y. Okay? So therefore, first thing to do is to sum up forces along x or maybe along y. So we have to use these two equations. Z, no need to use this one because, as I've said, there is no force along z. So we have to use only x. So we will sum up all forces along y. Okay. What are the forces along y? Look at the free body. By the way, this is a free body diagram because these are the forces that act on this point. The point is the intersection of the string. So a free body diagram is a diagram showing all forces acting on it, on object. So our weight is directly downward. So therefore, this should be negative W. While T1, our T1 has a component along Y, and we have the component along X. So if you sum up all forces along Y, we need only to consider the weight and the component of T, which is what? Along Y. This T2 has no component along Y, so no need. There is the component of T2 along Y is 0. So therefore, do it. We have this T1 has a component along X, call it as T1X. Then for the Y component, call it as T1Y. So if you construct the first polygonal base, the first polygon of T1, now take note that if this is 30, this is also 30. That is the law of geometry. If this is 30, this is also 30. So constructing the first polygon of T1 in terms of its component, then this is the result. From the tail of T1, horizontally construct the x component with magnitude and direction, then connect the tip of the T1x to the tail of the T1y, then construct it horizontally towards the tip of the T1. So we are creating a right triangle. This is 90. Why? Because this is horizontal and this is vertical and this is inclined. So this is the first polygon of T1. This angle is 30. So therefore, we can always express our T components along Y in terms of T1. We can also express T1 in terms of T1x in terms of T1 because we have the angle 30 degrees. So we are now ready to sum up all forces. Look at the figure now. We can ignore this T1 because the image of T1 was replaced by T1x and T1y. So consider only the yellow, the coordinates of the image. So the forces along y, we have only two, weight downward and the T1y, and this is positive. So sum up everything along y. So sum up everything along y. This is positive T1y, y positive T1y because this is upward. Why is it that W is negative? Because this is downward. There are only two forces, then equate this to 0. It must be set to 0 so that we ensure that the forces along y is equal to 0. So, therefore, T1y transposing W to the right side. Okay, but before that, T1y, look at the force polygon, the right triangle. T1y is adjacent. Okay, if you take cosine of this angle, it is adjacent over hypotenuse. So solving for T1x is T1 sine 30. Recall your trigonometry, the right triangle principle. So therefore, substituting the angle, okay, so this is T1 sine 30, then equal to W, okay, transpose W, then W is mass times gravity. So then, divide both sides by sine 30, then the answer is 147.15 newtons. This is the tension of tensile force exerted by T1. The T1 is this string. So this string exerts the amount of 147.15 newtons. The direction is away from that point. So we already solved T1. What about T2? Okay, T2, again, remember that we use this summation of force along y is equal to 0. Then this time, we use the summation of x along 0. So, what are the forces along x? Summing up all forces along x should be 0. So, meaning identify all the forces along the x. So, what are the forces? Look at the free body diagram. You look at the free body diagram, again, in the x-axis, there are two forces. We have T2 towards the right, and we have T1x towards left. Forget the T1 because, as I've said, the image of T1 are T1x and T1y. So, ignore this one. So, therefore, there are only two forces also along x. So, the T1, T2 is positive, and this is T1x is a negative force. So, do it. T1x negative plus T2 positive. These are only the forces. So, therefore, set this to 0. Now, remember T1x. T1x. What is T1x? Okay. There's a discrepancy. Sorry, this is sine. This is Ty. Ty. So, therefore, this should be opposite over hypotenuse. So, this should be sine. Sines. Okay, so this is still 147, 47.15. Okay, now this time we are now looking for the value for T1x. This is T1x. So the T1x is adjacent to 30 degrees. Adjacent to 30 degrees. So therefore, it should be cosine. Okay, kindly correct for my first statement here. This should be, okay, this is correct sine, and this is cosine. Cosine is because the T1 is adjacent to T1x is adjacent to T1. So therefore, okay, so take note that we already solved T1 here. So T1 is already 147.15. So substitute this value here, then solve for T2. So solve for T2. T2 is 147 because we will transpose that to the right side. So 147.50 cosine of 30, then it is equivalent to 127.43 newtons. So therefore, these are the answers to the problem. The T1 has a tensile force of 147.15, while T2, it has a force of 127.43 newtons. Okay? So, in order to practice yourself, uh, try this. Calculate the tensions in the string. So, what makes this problem different before we solve this problem? If you remember, our second string is horizontal. This time, we have the string inclined at an angle of 60 from the horizontal. This is still 30. This is 30 degrees, and this is 30 kilograms, and this is 60. Question: what are the tension in the string? So again, solve this one. Say T1, then T2. This is still our weight. So nothing to worry with the string because this is equivalent to weight. So okay, good luck. That's all. Thank you.